Welcome everyone. Today we are going to talk about confidence intervals. When the mean or proportion of a population is not known, which is usually the case, it can be estimated with a confidence interval. A confidence interval gives us a range of values that likely contains the population value. This is our investigative question: if you toss or drop a Hershey's Kiss onto a surface, how often do you think it will land on its base?
I think all the time, since the base is flat.
That's a good question. I'm not sure.
I think it will land on the base about 50% of the time.
We do not know the precise answer, but we are going to do an activity to collect data, and then use some statistical tools to help get an estimate. It is impossible and impractical to drop every Hershey's Kiss. In order to find out the proportion that land on their base, you will just take a small sample of dropped Hershey's Kisses in order to find out. Let's begin the activity.
9 out of the 35 that I have dropped landed on their base. So my proportion is about 0.26.
I have 15 out of 35 that landed on their base, so my proportion is about 0.43.
The proportion I got was close to the proportion that Susan got. I got 0.29.
My proportion is only 0.17. Our samples are the same size. Why are the proportions so different?
This is an example of sampling variability. It could be that the Hershey's Kisses vary slightly in size, and that affects how they land.
Or, each of us could be dropping them a little differently. Holding the cup a different distance from the table, or throwing the kisses rather than dropping them.
That's correct. Every sample is different, so the values of your sample proportions will vary. If you all place a dot that represents your sample proportion on the dot plot in the Google Doc, we will see this very clearly. Here is the dot plot of the sample proportions calculated by everyone in the class. What does this tell us? Russell, what do you think?
There are many different values on the graph. It's still not clear what the answer is.
It looks to me like the mean of the distribution is at about 0.37. Wouldn't that be the population proportion?
But we don't know if this set of samples is a complete representation of the entire population. We only have 30 samples.
The proportion of the population is not necessarily the value that appears most frequently in the sampling distribution. Karen has a good point, that we only have 30 samples. If we had many more samples in our distribution, then we would know that the proportion of our sampling distribution would be approaching the population proportion. Since we can only get a limited number of samples, we need another tool to help us estimate the population proportion. That tool is the confidence interval. We can take each of these values and calculate a range around it. That range, or interval, of values, is what we are hoping contains the proportion for the population of Hershey's Kisses. If, for example, we create a 95% confidence interval, then we can be 95% confident that it does contain the population proportion. Let's take a look at the formula. Here is the formula that you will be using to calculate your confidence interval. This value is called p-hat. It is the sample proportion that you just finished calculating. This is z*. It is the critical value, which depends on the confidence level. Since we will be calculating 95% confidence intervals, the z* critical value needed is 1.96. This is the standard deviation of your sample.
It looks like it depends on our sample size and the sample proportion that each of us calculated. So the standard deviation will be different for each of us.
Yes. Good observation. The critical value and standard deviation together make up the margin of error. The margin of error accounts for the variability of your samples.
So the larger our sample size is, the smaller the standard deviation is going to be. Which means, the margin of error will also be smaller.
That's great that you are seeing that, James. The size of the margin of error has an impact on the confidence interval.
Wait a minute. I don't get that. The sample size affects the margin of error? How?
I can help. If you look at the standard deviation piece of the equation, you can see that the sample size, represented by n, is in the denominator. So a larger sample means that we are dividing by a larger number, which makes the whole fraction smaller. That means that a larger sample size results in a smaller margin of error.
Oh. I get it. Thanks.
Now that you have done your calculations, let's look at how to represent your confidence interval.
I got 0.145 for my margin of error. So after I add and subtract this from my sample proportion, which was 0.26, my interval goes from 0.115 to 0.405.
So what do you think Susan's 95% confidence interval tells us?
There is a 95% probability that the proportion of Hershey's Kisses that land on their base is between 0.115 and 0.405.
I think it means that 95% of samples will have a sample proportion between 0.115 and 0.405.
But doesn't a confidence interval tell us information about the population, not the samples?
Since this is a 95% confidence interval, this has to be connected to our confidence in the calculation.
This is a great discussion. A confidence interval is not a probability and it does give us information about a population, not a sample. The correct interpretation of this interval is that Susan can be 95% confident that the proportion of all Hershey's Kisses that would land on their base is between 0.115 and 0.405. Now that you have calculated your confidence intervals, please enter them in the Google Doc, so that we can see what the collection of intervals for the entire class looks like. Here is the completed Google Doc with everyone's confidence interval. Notice how each interval is centered at your sample proportion.
It also looks like the intervals are not all the same length. That would make sense, since we expect the margin of error to be different for each sample, as we discussed earlier.
If we take many samples of the same size from this population, about 95% of them will give us an interval that contains the population proportion. So it looks like our estimate for the population proportion is most likely between 0.3 and 0.4. Well done everyone.